Do that one. Fantastic. I'm so excited to be here. So about a year ago, I got the title of doctor, and I thought nothing would ever be as exciting, but tonight I am the Scarlet Satellite, which is almost just as good. And I'm here to talk about the objects nearest and dearest to my heart, the universe's tiniest star-forming factories, or dwarf galaxies. Which is not LEGO, so I'm sorry. So, this is not a dwarf galaxy. In fact, the Admiral Galactic Nuclei, I showed this image earlier. So this is what galaxy? Anyone? Andromeda, of course. You guys are smart, audience. It's the nearest massive galaxy to our own galaxy, the Milky Way. And it's actually very similar to the Milky Way in many respects. Similar mass, similar satellite population. I'm going to talk a lot about the Milky Way, but I'm going to use this picture instead. Can anyone tell me why? Yeah, because we can't see the Milky Way like this with this nice, beautiful image. At least not yet. We can't quite get far enough away to take this beautiful shot. Okay, so before I get into dwarf galaxies, though, I'm just going to give a brief intro, talk about what I'm going to refer to as the standard paradigm, standard cosmological paradigm, just the basic theory for galaxy formation, our best guess, our best theory for how galaxy formation works. And that is, all galaxies form inside what we call dark matter halos. Big, giant, spherical masses of this mysterious substance called dark matter. Now, the Admiral showed a big blue sphere. Mine's a cloudy, sort of blue, nebulous object, but it doesn't really matter because these are just artists' renditions. We don't know what dark matter looks like because we can't see it. We can't actually, even though galaxies live in these, we know they do, in these big balls of dark matter, we don't know what kind of particle dark matter is. And in fact, we don't even know if it's a particle. But we know it's there. And that's because dark matter interacts gravitationally with normal matter, with the gas and stars and galaxies, with you and I, but only gravitationally. And so you might, maybe you guys are skeptical, like, we can't see it. I've heard this a lot of times. We don't know it's there. How do we know dark matter is there? So if you have a little trouble accepting how we can know something is there without seeing it, imagine this. You're in a dark room. In the distance, you see some swirling glow sticks. This looks like an audience that's seen some swirling glow sticks in the dark. And all you can see is the light from those swirling glow sticks. That's it. But you know, because you know a little bit about the ways of the world, that there's almost certainly some strings attached to those glow sticks. And either a person or a robot or something is holding and swirling those glow sticks. And you know that the strings have to be strong enough to keep those glow sticks from flying off into space. So that's like dark matter. And you know that the faster and faster and faster those glow sticks spin, that must be some pretty strong string, right? Imagine them just spinning so fast. You're like, that is some strong string. Is that chains or something? Because you know, if there wasn't something pulling those glow sticks towards the center, they would fly off into space. Well, it's just like galaxies. Especially at the outskirts, galaxies rotate faster than they should be able to if the only thing pulling them in were the gravity of what we can see. So there must be some other mass that also has gravity, that also pulls on normal matter with gravitational, through the gravitational force. That's what we know as dark matter. Now, dark matter may be difficult to detect. We haven't detected it, but it's super easy to simulate. And so the earliest simulations that simulated huge chunks of the universe only simulated dark matter, because once you get into gas and star formation and all that, well, it's a different sort of game. Dark matter, because it only interacts through the gravitational force. We know the gravitational force law. We can stick it into the best supercomputers in the world, and we can run and we can simulate the dark matter distribution for huge chunks. This is about 40 million light years across. And each little purple dot here is one of those dark matter halos, which according to the standard paradigm, as I told you, has what in the center? A galaxy in the center. So each one of these little purple dots should have a galaxy. Now, this is such a good prediction on large scales that I'm going to show two images here. One of them has taken a simulation, much like I just showed you, and placed a galaxy inside each dark matter halo. It's really easy. You just take the biggest galaxy, you put in the biggest halo, and you come up with a simulated image of a chunk of the universe, 3 billion light years across. The other is an actual image of the universe and the distribution of galaxies. So let's have a show of hands. We're going to look for what's the real universe. Is it on the right or left? Left to you guys? Red, red. Who votes red? All right. Who votes blue for the real galaxy? All right, yeah, okay, that's exactly what I wanted. Some people, those of you can cheer yourselves for who is right. But even if you knew, even if you're little smarty pants and you knew which was which, because you study SDSS all the time, the two images are statistically indistinguishable. And so across the largest scales in the universe, over billions of light years, this sort of standard paradigm of dark matter and galaxies forming inside of it does a really fantastic job of matching the known universe. But I'm not here to talk about the large scales, that's boring. I'm here to talk about where it kind of breaks down. The smaller scales, dwarf galaxies. So going back to our dark matter only simulation, one of the predictions of the standard paradigm is that dark matter is hierarchical. These big clusters, so this is what we might form a supercluster, have little clusters inside of them. The clusters have halos. The halos have subhalos. And so if we take a chunk of this, we take a dark matter halo that we would expect to host something like our own Milky Way, and that's a dark matter halo of about 10 to the 12 solar masses. If we zoom in, we can see that dark matter is truly hierarchical. This is another dark matter only simulation. It's the Via Lactea simulation. And basically, this dark matter halo, our own Milky Way, remember, we're Andromeda, is supposed to live right in the center of it. It's not to scale. But you can see that it predicts thousands and thousands of tiny, smaller other subhalos orbiting in and around it. And so if we just blindly follow what I've been calling the standard paradigm and put little galaxies into each and every one of these halos, we would see, now when we look up out of the night sky, we're going to see, what, thousands of dwarf galaxies? Not exactly. All right, who knows how many dwarf galaxies we do see? Anyone? 100, 1,000, 7? 2? 2. You can see 2 with your naked eye. That's good. That's right. But how many have been discovered, roughly? Tens, hundreds? Tens, yes. 40, I think it's actually a little more. I heard someone say 50 recently. A bunch of them have been discovered, the smallest ones in just the last few years. The two biggest ones, the large Magellanic Cloud, the small Magellanic Cloud. If you look at the name, you can see a lot of familiar. You got your Leos, you got your Ursa Major, you got your Booties, you got your Sagittarius. So what are these? Does anyone have a guess for what dwarf galaxies are named after? Their horoscope, right? I mean, they need to know under what sign they were born. So obviously, we name them according to their horoscope so they have an easy time. No, it's the constellations, or mostly, usually. Okay, so there are about 40 to 50 dwarf galaxy satellites, when the standard paradigm should predict that we have thousands. So this is a tension. It's a problem called the missing satellites problem. It's a very old problem with probably more solutions than I'd care to get into, but it's still a tension. And there are two main reasons why it's only a tension and not a nail in the coffin for the standard paradigm. The first is, well, okay, we know that the biggest subhalos should probably host galaxies, and we have enough to fill up the biggest ones, right? So you could take those 40 galaxies, just start plopping them into big subhalos. I'm not gonna, I'm only gonna do 7, but you get the idea. The next reason that it's probably okay is that the smallest, the tiniest little ones, the tiniest little subhalos, we don't believe should have ever formed any stars or any galaxies at all. And that's because early in the universe, when the first stars formed, the radiation from those stars blasted the gas out of the potential well. They didn't have enough gravity to hold onto their gas and just blasted it out. And so we don't think the smallest ones should have formed any galaxies. But what's crazy to me, or intriguing to me, or is keeping me in a job, is that still today, in 2017, we don't know what the lowest mass dark matter halo is that can form a galaxy. We don't know if it's a hard cutoff. We don't know what that mass is if it is a hard cutoff. The number that's kind of been tossed around is 10 to the 9. Yeah, so we don't know what's the lowest dark matter halo. But particularly, the number that's been thrown out as a possible cutoff is around 10 to the 9, around a billion solar masses. And so specifically what I wanted to look at is it possible to form a galaxy in a dark matter halo lower mass than 10 to the 9? And if these tiny galaxies exist, I mean, can we even see them with current technology? If a prediction is not testable, then why make it, right? That's the scientific method. Okay, so to do that, I'm going to run a different kind of simulation. Every simulation I've showed you so far has been dark matter only, because that's easy and you can make it really big. But it's failing so far for making these kind of predictions. So I run simulations that actually have star formation, physics, and if I wanted to do that for a Milky Way mass halo and still have the level of detail required to form tiny satellites, well, I would have to, I don't know, be the president of NASA or whoever gets to make all those calls. I don't have that kind of computation time, so I'm going to cheat a little bit, sidestep, innovate, and I'm going to take one of these smaller subhalos of the Milky Way and zoom in yet again. Because the more you zoom in, the standard paradigm predicts that you keep having substructure. This is a dark matter halo of about 10 billion solar masses. And it too even has little subhalos. Oh, whoops. It too has little subhalos, and some of them are lower than that 10 to the 9 solar mass scale that I'm interested in. So this is one of those 10 to the 10. We just took a dwarf, we zoomed in 10 to the 10. This is the gas temperature that you can see here. And the simulations I run are called FIRE, Feedback and Realistic Environments, whatever. We love our acronyms in astronomy. There's a whole business. I think you could get a job if you could make the best acronyms for other astronomers. So, but in addition to dark matter and gravity, I have gas physics, star formation, stellar evolution, and supernova explosions, which you can actually see in action, blasting the gas out. Every time the gas goes, that's the supernova going off. But, okay, so the simulations are cool, awesome. You always got to have the requisite simulation video to wow your audience. But what does it say about satellites, right? That's what we're here. What does it predict for tiny satellites? Now, this is the dark matter distribution of my simulation. I haven't put the stars up yet, but, you know, just so you're wowed by the appropriate thing on the screen, I should point out that we know exactly what's going to form in here. We know that it should form about 1 million solar masses and stars. That's known. What we don't know is if any of these, specifically this guy, any of these other little subhalos that are lower mass, below 10 to the 9 solar masses, will form any stars. Let's see. Okay, well, come on. I was expecting maybe some jumping and cheering, or at least, come on, we got a little tiny scarlet satellite here. Yeah, so my simulations actually do, this round of simulations does predict that tiny galaxies form in dark matter halos less than 10 to the 9. Now, these tiny satellites are only about a few thousand solar masses. This is very small, so then the next question is obviously, okay, can we see a galaxy that's made up of only 3,000 stars? Because as you get smaller and smaller, lower and lower mass, galaxies become more difficult to see. This is the Large Magellanic Cloud. How many of you have seen this with your naked eye? This is in the southern hemisphere, so it's not easy. You can see this one and its cousin or brother or whatever partner, the Small Magellanic Cloud, with your naked eye if you go away from some light in the southern hemisphere. If you ever get a chance, I recommend it. It's pretty cool. And it is 1.5 times 10 to the 9 solar mass and stars. It's pretty big, right? It's like just a pretty big fraction of the Milky Way. As you go lower and lower mass in dwarf galaxies, they become harder and harder to see, at least with your naked eye. This is Leo 2. 10 million solar masses and stars, but you can still see it here. Keep going down. We have 100,000 solar masses and stars. Booty's 1. I can't see that. Can anyone see that galaxy there? If you can see the galaxy, come see me after my talk. I might be able to get you a job. But the thing is, we don't need our naked eye to see these galaxies. There are new instruments and surveys coming online that are doing star counting, sophisticated analysis, such as the Dark Energy Survey, which has found a large number of the tiny ultrafaints recently. The Hypersuprime Cam on Subaru has also detected tiny things as small as a few hundred solar masses. This is 1/10 of the galaxies that I even predicted. However, we don't know, just from these observations, it's really hard to measure the dark matter halo. So we don't know if my predictions yet are correct. They have not been falsified or confirmed. We have not yet detected a galaxy and confirmed that it's in a dark matter halo mass less than 10 to the 9. We have also not found an ultra-faint satellite confirmed to be a satellite of another dwarf. All the ultra-faint satellites that we know, some of them might be satellites of the LMC, maybe. We don't know yet, but most are satellites of the Milky Way. So the important point I guess I want to make to you now is I made some simulations. Maybe, of course, they're the best in the world yet to date, but they are just one set of simulations with one set of assumptions. And they have predicted the existence of these satellites, but they may not exist. Other simulators, other codes, and I'll be honest, maybe even a few of my own simulations I've run since then, aren't actually producing these satellites. But the cool thing to me is, if you tweak just a little bit of the numerics, a little bit of the physics, it either makes a prediction for these satellites or it doesn't. So if we can find them and we can confirm that they live in these tiny dark matter halos, it would help us make the best simulations possible, help us know what physics is right, what physics is not right, and we can learn a lot about the standard paradigm, about galaxy formation, and about the universe as a whole. Thank you.
All right, thank you, Scarlet Satellite. So you're going to want to stick around for questions because this is going to be great. Questions up top? All right, right up there.
On the small halos you're looking at, do any of those correspond with globular clusters?
That is a fantastic question. So the question is, in our simulations, do any of the small halos correspond with globular clusters? What I think you mean is, are we forming any globular clusters in the simulations? Right. Yeah, no. Yeah. So the crazy thing, and it's an outstanding problem, and I know a certain professor at UT who has maybe declared that it is impossible, because of the numerics of the simulation, to form globular clusters. We have not yet formed them. I'm running simulations right now that we've twiddled a few things with the goal to see, like we've increased the density requirement for forming stars. It's hoping that a bunch will form in a cluster. So far as I know, we're not forming them in simulations. It's a big problem because they exist in the real universe. So we're still working on that, and we'll get back to you, because if we can form them in simulations and figure out what makes them form and what makes them not form, because they exist in the universe, we'll know we're on the right track or not.
All right, more questions. We're going to stay in the upper deck.
Yeah, I think there have been some, I don't know if it's confirmed, but there have been some very strong evidence for intermediate mass black holes at the centers of dwarf galaxies. I've thought about running simulations to put them in. I haven't done so yet. Possibly some people have. But yeah, I think there is some evidence, and I think it would be interesting to run. We have the ability. We put them in our more massive galaxies, but in my group at least, we haven't yet done that. But it's something that's for the future.
All right, next question. All right, we'll go in the back.
We don't. Yeah, I mean, the question is, could dark matter be strange matter? And I don't know specifically what you mean, but dark matter, I mean, it really could be anything. Like, if you consider standard model, if you wanted to either adhere to the standard model or match up to the standard model in some prescribed way, we're basically ruling out parameter space of where it could be, but in the end, I mean, it really could be anything. Like, people are coming up with even new, more out there, the more we're ruling out our kind of known parameter space of possible standard model and other particles, the more we rule that out, the more people are looking at completely, and it could even, I mean, it could in theory not be matter at all. Like, there's other, alternative forms of gravity. Like, in the end, we think we're sticking to what we think is the most likely, what matches the most observations, and that has it be some sort of particle dark matter. But I think it's important to keep an open mind and keep checking all the possibilities.
All right, I saw you first.
So do we know what causes the distribution of dark matter, or are we just looking at a correlate with where galaxies are and it's not there?
Yeah, no, that was the question is, do we know the distribution of dark matter, or do we kind of like set it up to match in some way? So no, I mean, the answer is we didn't know that. It comes from basically the idea is that, for the Big Bang Theory, early on there were these quantum fluctuations in energy density, and inflation, which is one of the things that it solved. It blew up those fluctuations into macroscopic fluctuations. A bunch of very smart people calculated this all on a pencil and paper, and we all, we use that as the initial conditions of our simulations. We don't a priori set it to match any sort of galaxy clustering, so that's actually one of the successes of the model.
Okay, one more question.
Upper right,
I
upper
can't
right.
see anyone in the
Upper
front
right.
row, so
right.
I'm going to go front row. Okay. Go.
So in your opinion, would a better understanding of quantum physics put us closer to understanding dark matter?
Probably. Sorry, the question is, would a better understanding of quantum physics put us closer to understanding dark matter? If it's a particle, yes. so probably, since I think it probably is. So in most scenarios of what I think dark matter probably is, yes, there's an absolute particle physics angle to figuring out what it is. We're working now in our simulations to make dark matter more modular, so you can put in your little specific particle physics quirk and run a simulation and see what that predicts. Working more in line with the particle physicists to test different kinds of dark matter. So I think it's not necessary, but almost certainly.
And we have future talks planned in terms of alternative dark matter models in this scheme here, so stay tuned for that. And sir, up there, will come down and ask us questions right after that talk. We got to wrap up here. So let's thank Scarlett Satellite one more time.